Got it. All right. So let me just read that one more time. So enolate ions can be looked at as either a vinylic alkoxide or as an alpha keto carbanion. The lesser known reaction, the reaction that doesn't happen as much, is on the oxygen. The reaction on the oxygen yields an enol derivative, but more importantly, what we will focus on for several lessons is the reaction on the carbon, the carbanion, and it yields an alpha substituted carbonyl compound. We've already seen an example of that with the halogen substitution. The reaction on carbon yields an alpha substituted carbonyl compound. Okay, we've seen it in the lesson from yesterday, or I guess it was Wednesday, that you can substitute a bromine or another halogen like chlorine or iodine in the alpha position. But another common thing is you can do an alkyl substitution. So you substitute the hydrogen, okay, with an alkyl group. Okay, again, we're not going to look too much at this one where you have the alkylation on the oxygen. We're going to focus on the carbon being the nucleophile and reacting with the through an SN2 mechanism, reacting with the alkyl group of an alkyl halide. Okay, so it's base promoted, so we got to rip off, we got to put a strong base in there to rip off that hydrogen to create the carbanion, and then that carbanion will be a nucleophile and will attack that alkyl group through an SN2 mechanism. Okay, now there are some limitations. So that's what these, brackets and abbreviations are for. So typically the leaving group, so it's an alkyl halide, but it can also be a tosylate. Okay, now I'm going to bring up the structure of tosylate just to remind you what it is. Oh wait, not yet. Okay, but the X has to be a good leaving group. So something like a large halogen, chlorine, bromine, or iodine. Okay, and even tosylate, and again, in the next slide, I'll remind you what tosylate is, what it looks like. So that's the kind of alkyl halide that it needs to be. But it also needs to be either a methyl, a methyl group, or it can be a primary alkyl group, or it can be an allylic or benzylic group. Okay, so it's kind of that order of reactivity. It's even more reactive if it's allylic or benzylic, then a methyl, and then the primaries. So it doesn't really follow the same sequence we've looked at before, where, like a tertiary and then secondary and then primary and then methyl. It doesn't really follow that kind of pattern. So it's just one of those things that you just need to know what the limitation is. This will not work if it's a secondary alkyl halide or a tertiary alkyl halide. This type of reaction will not work. And if you have some leaving group other than these, tosylate or a large halogen, this reaction will not go. Okay, so as I said, part of the reason why it's limited is because of the mechanism. The mechanism is an SN2 reaction. So that means that, first of all, there's got to be a pretty good leaving group in order to have this mechanism. Okay, and also, just to, as I said, I'm going to remind you what tosylate is. That's the structure for tosylate. You don't need to draw this or anything, but if this leaves, if the electrons in this bond move onto the sulfur, it's resonance stabilized because it can go through the ring, it can go to the oxygen, so it's delocalized heavily. So that's why tosylate is a really good leaving group. So the electrons between this bond would just hop onto the sulfur and then get stabilized, delocalized through resonance forms. Okay, so that's one limitation, is that because it's an SN2 reaction, you need a good leaving group, but also because it's an SN2 reaction, you have to think about steric hindrance. You have to think about crowding. And so that's why it really only works with a primary alkyl halide or a methyl. And the reason why it really works well with an allylic or benzylic group has nothing to do with crowding so much as just the resonance stabilization again, but we don't get into that too much. But as I said, it doesn't really work with secondary alkyl halides. And with tertiary alkyl halides, it's safe to say it doesn't work at all because there's going to be a competing reaction where you get the elimination, where whatever the leaving group is will leave at the same time. A weak base will take away a hydrogen and give you that alkene product. But the point is that you got to limit it to a methyl, a primary alkyl halide, or also works with allylic or benzylic alkyl halides. Okay. So here's some examples of this reaction occurring. So again, I mentioned that we're going to start using this base, LDA, lithium diisopropyl amide. Okay. And we said the reason why it's used is because it works. It's soluble in organic solvents and it does what we want it to do. So it is what removes one of these acidic hydrogens. And remember, the reason why it's acidic is because it can form that carbanion that's stabilized with the nearby carbonyl group. Okay, so that delocalization of that negative charge makes it more stable, so it makes those hydrogens more acidic. Okay, more acidic, for example, than the two hydrogens here on this carbon or the two hydrogens here on this carbon. The reason why these are preferentially removed by a strong base like LDA is because that resonance stabilization that you get from the resulting carbanion, the conjugate base. Okay, so then we are going to react that. Here it is. It's a methyl iodide. So this is an SN2 reaction where that pair of electrons attacks the carbon. Okay, and the iodine is the leaving group. And so you're forming that bond with the methyl. So that attacks the carbon and forms that bond. Okay. Now this also works not only with ketones like, well, okay, this is a lactone. Sorry, this is a cyclic ester. Here's just an acyclic ester. Same thing. So you remove this hydrogen because it's the most acidic, and then the carbanion attacks the methyl. The iodine leaves, and you form that new bond, that new carbon-carbon bond. So we did an alpha substitution. Again, this is the functional group, and alpha to it, right next to it, is the methyl. So it's an alpha substitution. Okay, here's just two more examples of that. They're also just printed in your handout. But what I'll say about this one, so first of all, you might wonder, well, wait a minute. So these are both alpha positions. Let me actually make note of some of this on the, okay. So that's an alpha position right there, but that's also an alpha position. So why is it that the LDA will preferentially react with one of these hydrogens rather than this hydrogen over here? And the reason why, again, is because of crowding. This makes it, more crowded. So it's too crowded for that LDA to approach this alpha position. So it preferentially rips off one of these hydrogens just because they're more available. Okay, so that's why we get 56% of the product when it removes one of those hydrogens, and only 6% of the product when it removes the hydrogen from that other alpha position. Okay, so it does happen. You will get a mixture of products, but it happens much more with these two hydrogens on the right because they're just more accessible, easier to remove those with the strong base. Okay, and just to, I guess, make the point that you don't only have to use a carbonyl compound, but like a nitrile, any sort of electron withdrawing group can make these hydrogens more acidic. And so it has applications beyond carbonyl compounds, but we don't get into that in this lesson, just making the point. All right. Okay, so let's do an example question here. It says, all right, so show how the compound given below might be prepared using an alkylation reaction as the key step. Okay, so we want to see, and think about, it's kind of reverse engineering. We want to think about what might have gotten added. Okay, well, here's your alpha position, right? So maybe instead of a methyl group here, maybe there once was a hydrogen here that got removed. So let's draw that as our starting material. And if you don't mind, I'm going to abbreviate this just because I know I have really bad handwriting, and drawing benzene rings makes it worse. So let's just say that I have the phenyl group, right? That's the abbreviation for a benzene ring when it's like a substituent. And so that, as I said, is connected to a carbon with now two hydrogens. And so that's connected to our carbonyl. And we got the methyl group. Okay. And so then, let's say it's reacting with LDA, but I'll go ahead and kind of draw out a little bit of the structure of the reactive part of the LDA. It's an amide, so it's diisopropyl, but I'll just put R group so I don't have to draw the isopropyl part. But that negative charge, because it's got the formal negative charge, it's got 2 lone pairs, that's a really strong base. It's going to grab that hydrogen, which is going to dump its electrons onto that carbon. Okay, and then there's, you know, just the lithium counter ion out here to balance the charge. Okay, and so then that's the step where we create the carbanion. So I'm just going to draw that intermediate. So now I've got this carbon still with 1 hydrogen on it, but now it's got a lone pair and a negative charge, what's next to the carbonyl. And I'm only going to draw this 1 resonance form, but remember that that lone pair of electrons, that negative charge, can get delocalized with that carbonyl, and that's what makes it stable, or somewhat stable. Okay, so then that's going to react with, like I said, a methyl iodide, for example. So that reacts with the carbon, which dumps the electrons from the bond of the methyl group with the iodine onto the iodine. So it forms a bond with the carbon, and then we get our other product. Okay, and again, just to account for everything, at this point, I've got lithium iodide as a byproduct, and I've also got the protonated, you know, diisopropyl amide as the other byproduct. Okay, so I think that what happens next is something with better penmanship shows up. Let me just double check that. Yeah, there we go. So if the overall reaction, it doesn't include the intermediate step. Okay. So now what we're going to do is I want to draw. If you want to find some room on the back of a piece of paper or something, you can draw along with this, or if you just want to follow along, just, you know, we're going to do several of these in the notes, but I just want to kind of set the stage with a simpler mechanism. Okay, but let's say that I have this structure right here. I'm going to draw a, well, let me just draw it. So let's say that I got a carbonyl, and oops. Okay. So I got the carbonyl, and I'm going to draw it as a carboxylic acid, but I'm going to draw it a little differently than I normally do. So that's a carboxylic acid functional group. And then I'm going to draw a connection to a carbon there, and let's say this carbon has some other R group attached to it, and then a hydrogen attached to it. And then that's attached to another carbonyl, which I'll draw like this. Okay. Okay, so that's kind of our starting point. And notice that it kind of makes a 6-membered ring. I did that on purpose. I drew this potential 6-membered ring, the center stage of this molecule. Okay, so now, these, as the title says, you know, the decarboxylation, that's a big fancy word we'll explain in just a second, but this one is important. So of the beta keto acids, I want to explain what that beta keto acid means. All right, so here, of course, is the acid. So that's the acid part of that name. But then the beta, meaning that this is the alpha position, and then this would be the beta position. So you have this ketone part right at the beta position. So this is a reaction that occurs whenever you have this, whenever you have beta keto acids. And it could be other scenarios, but the big thing is in the beta position, you have that carbonyl. Okay, so I'm going to actually erase, I'm going to erase all that. No, I'm not going to erase all that. I'm going to erase that, that, because it's going to get a little bit messy. So if you want to redraw that, if you drew on that and you want to redraw that, I'll give you a second to do that while I take a drink. Okay, because I got to color code this. There's a reason why I'm doing it this way is because I want to kind of color code this. All right, so I'm going to just try and illustrate what bonds are going to be formed and what bonds are going to be broken here. So let's do this. Let's do like a purple. Okay. So you can see that there's kind of going to be a hydrogen bonding interaction here between this oxygen and this hydrogen, right? We know way back from general chemistry that when you have that oxygen connected, or the hydrogen connected to an oxygen, nitrogen, or fluorine, and it's nearby the lone pair of another oxygen, nitrogen, fluorine, you get hydrogen bonding. So there's a hydrogen bonding going on right there between those two atoms. So in order to, or what might happen because of that is that hydrogen might pop off and form a bond with that carbonyl oxygen. And where it's going to put its electrons is it's actually going to move its electrons down here to form another C double bond O with that oxygen, okay? All right, so let me change colors again. Okay, so as I said, what's going to happen is this oxygen, because of this hydrogen bonding interaction, is going to basically form a bond between the oxygen and the hydrogen, and those electrons are going to come from this pi bond here. So with green, I'm going to draw an arrow right there. So I'm going to form a bond between that oxygen and that hydrogen, and the electrons that make that bond are going to come from this pi bond here. Okay, I'll change colors again to a dark blue. All right, but now if you do that, then what you've got over here, because that hydrogen is gone, remember we're going to break this bond. So now it's just CO2. Well, we know what CO2 is. CO2 is carbon dioxide, a very stable, very common gas, which is kind of a good leaving group. So it might want to exist on its own as CO2. And that's indeed what happens. That's what decarboxylation is. So in order for that to happen, though, I've got to break this carbon-carbon bond. So what becomes of that? Well, it basically skips over and forms a double bond between that alpha and that beta carbon. Okay, so that's the movement of electrons. Okay, so it's like they all just kind of move one over. Okay? So then, let me draw the structure as a whole again with the new bonds. Okay, so once again, I've got the carbon, the double bond to the oxygen. And so now I've got oxygen, and now I've got, did that one with purple, so I'll draw the other line with purple so you can see where that bond comes from. Okay, so that's your CO2. And then over here, I've got the carbon with the R group and the hydrogen. That's really messy. Let me erase that. Try that again. And so now I've got a double bond between these two carbons. And so the other one I'll draw with blue. So again, you can kind of see where that double bond comes from. And of course, it's got to be double bonded to that other carbon. Okay, so now this has a single bond with the oxygen and still has that single bond with the R group over here. Okay, but now it's got a connection to a hydrogen that I said, came from these electrons. I drew that in green, so let's change colors one more time. Okay, so what we generated here was we generated CO2, okay, and we generated an enol, right? An enol, okay, which we know is stable because it's got that tautomerization as well. The resonance forms, or it's not resonance, but it's like resonance. It stabilizes it, okay? All right, so now, having done that, I think we're ready to move on to our, more of a discussion on decarboxylation. Okay. All right. Okay, so what is it? Well, decarboxylation, what it requires, first of all, what does it require? It requires a carbonyl group 2 atoms away from this carboxylic acid group. Okay, so 2 carbons away from the carboxylic acid group. Or pardon me, 2 atoms away from the carboxylic acid group. Okay, and so part of the reason why I wanted to, trace it out atom by atom, step by step, is because I think that's easier to see the mechanism here, where they've just reproduced what I did with the color coding earlier, but they just don't have as much color coding. So what we actually looked at was this reaction down at the bottom here. Okay, the beta keto acid, where we have the carboxylic acid group. Okay, and this oxygen is attracted to this hydrogen, so it takes some electrons from this double bond, forms a bond there. It's that bond there, that bond there. Okay, in order to make the connection with this oxygen, we got to break the connection with this oxygen, so those electrons get dumped into that CO2 that's going to get removed. Okay, because that gives that a double bond, and we got this double bond, so that's your CO2. Okay, but then again, we also got to break that carbon-carbon bond, so that dumps those electrons and forms this double bond right here. What was a carbon-carbon single bond now becomes a carbon-carbon double bond. Okay, and then again, because that's got a tautomer between a tautomerization between the enol form and the ketone form. And you can do it with a diacid as well. That's what this is an example above here. And so we're going to look at another application of this in just a little bit. Okay, but it doesn't have to be a ketone. Here, the other carbonyl was part of a ketone. Here, the other carbonyl is part of a carboxylic acid. So it can work with other functional groups, but the two things you need is you got to have at least one acid functional group, and then 2 atoms away, you got to have the carbonyl group. That's the requirement. Okay. So you may be thinking that, well, the CO2 is the leaving group in this case. No, not really, because with the leaving group, every time we talked about that before, the leaving group is what takes the electrons. Well, in this kind of reaction, it's not the CO2. It's the rest of the molecule that takes those electrons. So it's really like the rest of the molecule is the leaving group. Okay? So why does this reaction occur in the first place? It seems pretty complicated. What's the driving force for this reaction? Well, what makes it favorable? Okay. So remember thermodynamics from Gen Chem 2, okay? The whole idea of entropy, how the second law of thermodynamics says that spontaneous processes increase the entropy of the universe. And so in this case, we are definitely increasing entropy because we're going from one compound breaking apart into 2 compounds. That is more disorder, more, sort of more molecules to spread the energy, to disperse the energy across. So that is an increase in entropy. But also the CO2 is a gas, and gases have a lot of entropy. So we increase the entropy of the universe, so that's part of what makes it favorable. But the other thing that is a consequence of this, and the reason why this reaction is pretty common, as complicated as it is, with all these electrons and arrows moving around, the reason why it's a pretty common reaction is because it turns out to be irreversible. Because you're generating this gas, that gas just floats away. So it's not in the system anymore to reform the original reactants. It can't happen because it floats away. So it's pretty much an irreversible reaction. All right. All of that to bring us to this point. So this is exploited and used extensively in just synthetic organic chemistry to do something called malonic ester synthesis. Okay, this is a common approach to make carboxylic acids. Okay. So first of all, what do we mean by malonic ester? Well, here's a diagram of it. It's already in your handout there. So one thing that can change that is variable are this part of the molecule. In this case, it's an ethyl group, but it doesn't have to be. It would still be considered a malonic ester, but it typically is. I think that this one is just easy to, produce, and it's stable, and so this is the most common one to use. Okay, so what do we do in a malonic ester synthesis? Well, what we do is we take an alkyl halide. Okay, so just, some alkane, or really, it doesn't have to be an alkane. It can be an alkene as well, but it just needs to have a halogen attached to it somewhere. And you make it into a carboxylic acid with 2 more carbons. So notice that whatever you started with, R, it's the same R, but now it has 2 more carbons in it. Okay, and one of those carbons is part of the carboxylic acid functional group. So this is just a very useful reaction to make a carboxylic acid by design. There may be some specific carboxylic acid you want to produce, and so this is a typical way to get there. All right, so here are the 4 steps of malonic ester synthesis. We'll look at the steps, and then we'll look at some examples. So first of all, you have deprotonation. Okay, so remember that this is your alpha carbon, deprotonation of an alpha carbon. So these hydrogens here in malonic ester, they're mildly acidic. Their pKa is fairly low. So we got to remove one of those hydrogens. Okay, so that creates a carbanion, which can act as a nucleophile. Okay, and so it will undergo an SN2 reaction with the alkyl halide. And then you can actually do this twice. Okay, because if there's two acidic hydrogens here, we can remove both of those with a strong base, and therefore, exploit that to really make a specialized carboxylic acid if we want. And then we learned, when we talked about esters back in Unit 2, at the end of Unit 2, we said that you can convert an ester into a carboxylic acid, and that's what we mean by hydrolysis, the acid hydrolysis. So I can convert both of these ester functional groups on the malonic ester into carboxylic acid, so that's step 3. And then all you need to do at that point is just heat it up. And one of those carboxylic acid groups will leave in the form of CO2. You can decarboxylate. Okay? So here's an example. I just want to draw some more things on here to kind of, again, just illustrate what's going on. Okay, so remember that this is going to be our strong base. So sodium ethoxide, the sodium has got the positive charge, the oxygen's got the negative charge. So this is our strong base. And so that is going to remove one of the hydrogens that's right here. These are the acidic hydrogens. So let's just say that it removes that one. So it dumps its electrons onto that carbon. Okay, and then if you don't mind, just to save some space and to save some time, I'm just going to say carbanion. Oops. The carbanion is just going to undergo an SN2 reaction right there. And so your leaving group in this case is going to be the bromine, so it leaves. And so, it's an ethyl bromide. So the bond that we formed is right there. Right, there's the two carbons that were right there. These two carbons are right there, and we formed that bond that I sort of highlighted in red. I'm not trying to draw a double bond, I'm just trying to highlight that bond as the bond that we formed. Okay? And so then, what we want to do is, we don't want these. We want to get rid of those. We want to get rid of those, right? So we do the hydrolysis. This is the ester hydrolysis part. Okay? And so you get the carboxylic acid groups. Okay? And so if you're following, this would be like if this is carbon 1, this would be carbon 2, carbon 3, carbon 4. Okay, so that in our product, that's carbon 1, carbon 2, carbon 3, carbon 4. So what we need to do is we need to split off this part. Okay, so this, we can just add the note, leaves as CO2. We decarboxylate it just by heating it up. Okay, also remember that sometimes they don't even write the word heat, that they just do the capital Greek delta. That's the other abbreviated way of saying you heat something, typically to reflux, whatever the temperature is that it boils at. Okay? All right, so that's if we do it one time. As I said, we can do this twice because there are two acidic hydrogens sandwiched between these carbonyl groups. So we can do it again. Let me erase all that. I'll advance the slide here. So this is a very common way to make a cyclic carboxylic acid because you can do this twice. So this just illustrates that process. So again, I'll pick it up from the second step here. So in this case, we still have this hydrogen here. Okay, so this, again, there's your positive ion, there's your negative. So that can take on that hydrogen, which dumps its electrons onto that carbon. Okay, and so then that does the SN2 at that carbon. And so you form that ring. And then you hydrolyze it, which basically you split off these to make it into carboxylic acid. And then when you heat it up, you decarboxylate it. So one of these carboxylic acid groups leaves as CO2. And then what's left over is the cyclopentane part and then the carboxylic acid on the other side. Okay, so this is just an example of what it would be like if this happened twice. Okay? All right. I think that's it. Hold on. Okay, so we'll stop there. Unfortunately, I don't have time to do any of the practice problems, but I will open that assignment for you guys to work on your own.